I'm Marcus Verviers. I'm doing security for I don't know, last 20 years. I've been part together with Eric in this review of Mullvad, and we thought that we bring this to the OSTIF because it's also let's say an open source project, and I think it fits very well into the topic of how to audit really complex applications that are crucial for internet infrastructure and security of everybody. But let me pass on to Eric to also introduce yourself.
Yeah, hi, I'm Eric. I only took a minor role in this audit. But I'm happy to present a bit with Marcus. We had two other team members, JJ and Ropje, who were part of this. And glad to be here.
Okay, then I guess we're going to jump right into it. I hope you can all see my screen share, my slides. We're going to talk about the security audit of Mullvad VPN and in particular about the client applications. To us, that's been a very interesting audit, as I said before, because it's an application stack that is across multiple platforms. It had been audited before because that's what they do. I think every 2 years at least. And the audit was, still kind of recent, end of last year. As Eric said, team of 4 people. In October, November. And of course, I want to say everything that we present here is already addressed. So Mullvad addressed the issues swiftly and was very cooperative in the audit, which is, I think, one of the main points even today. So the scope or what we were kind of asked to review are the client applications for different platforms, and there are a bunch of them. So you have Linux clients, you have Mac OS, you have Windows, Android, iOS. And we reviewed client applications, in particular kind of a shared code base and a daemon services. We reviewed graphical user interfaces, command line interfaces, and configuration. What was out of scope of this audit were all the servers, backend, and infrastructure, and also most of the dependencies, because as you will see, there's a lot of them, but we focused on really critical ones, and these had a spot check. The code is open source. You can find it on GitHub in this link. Slides will be shared later. Okay. On the bottom right, you will see why we didn't review all the dependencies, because there's a lot of them. There's also a huge amount of code. If you look at the commits, even over time, there's a crazy amount of code that is kind of scary, if you look at it, and also the rate that the code is being developed at, you can see as well, is super high. The code base is mostly written in Rust, modern memory safe language, also cross-platform. So Android, Linux, Windows, and OS X or Mac OS nowadays is covered, but there's also iOS, so there was also a bit of Swift code, and also, of course, dependencies and so forth. So there was a huge zoo of different programming languages, code, and so forth. And as you can imagine, full source code review, that was completely out of the question, even due to the size of that code base, due to the complexity, and also because by nature, the interaction of these applications is high with operating system, other systems, backend, and different protocols. So naturally, this led us to an approach that is not, let's say, the typical source code review, because it's just like impossible to review all that source code, which is more aligned to a white box pen test with source code access. I have to say that our team focused a lot of the efforts on actually reviewing source code. But we based that on a threat model that we developed beforehand and also agreed upon with the project. And doing that, we applied a lot of manual code review, static code analysis, but also a lot of dynamic testing, and also always came back to the threat model. Eric, do you want to say something about threat modeling?
Yeah, the idea about the threat model is to better understand the attack surface and where the threats actually might come from. And sometimes when working with open source projects, you are lucky and people already have something like a threat model. With Mullvad, I think some parts were already there from former audits. Quite often you don't have anything from the project itself, right? So you start to look at the documentation and get some pointers from there. Some things that you can base your threat model on is like common sense. And you can also look at similar products. I mean, there are other VPN products out there as well. So you could look at them and see what are their assumptions and can we transfer them to Mullvad. And in the end, make sure that you agree with the threat model that it's there, because sometimes developers might have a completely different use case in mind than their users. And they might have a threat model for one scenario, but the way the users are actually using the product is different from what the developer thinks. And that's quite often the case with privacy products, I guess. And yeah, in this case, we made sure that the threat model is something that Mullvad and we agreed on. Next slide, please. And this, we made sure to do this by having several online meetings where we went back and forth on the threat model. And we even made sure that we have time in the project to create a full threat model. Quite often you do it like quickly before even writing the offer, because once you know the threat model, you know what you have to look for, right? You know, do you need to look at the dependencies? Is there another way to target the application? And this might influence the amount of time you need. In this case, the threat model was part of the project. So we could spend a bit more time on that. And made it like not completely formal, but still detailed enough so we could work with it. Next slide. And when you look at a VPN client, at least one part for the threat model becomes quite clear once you start drawing a diagram that shows you the actors involved, right? You have your client that wants to connect to a peer. That's the item on the right. And it wants to connect to that peer through the tunnel. So you have the client, the peer, and the Mullvad relay that terminates the VPN. But you also have the internet provider involved. You have some third parties involved that do the routing. So you can get some parts of the threat model already quite easily from your network diagram. But there are other parties that might be involved that are not as easy to see. And one party might be another person on the client computer, right? If there's a second user account that might be compromised, is that something that you would consider as attack surface? And for Mullvad, this was quite clear. The target audience for the product is end users, and they can safely assume that there's only a single user in most cases, and all users on the computers are trusted anyhow. So they clearly define that a compromised second user on that machine or a compromised client is outside of the threat model. Another thing that's that you might want to look at is what about malicious people at Mullvad, right? So what kind of attacks could they perform? But that's also something that when you talk to the projects, you can see whether that's something they want to protect against or not. And in this case, that's also something that will be regulated in a non-technical way, right? I mean, if you have an attacker in the supply chain or something, that's nothing that you can prevent by modifying your code base, right? So these were not the things we were looking for, but we were looking for data leaking into the internet. Can attackers on the local network perform attacks that might leak data? These were the kinds of attacks that were then defined in the threat model. Next slide.
Yeah. That's something that I want to stress, that in this audit was let's say very helpful, and I feel like now I sound a bit nostalgic, but that has been a bit lost, I think, after COVID, is that in this audit we kind of went on site, and nowadays, meaning 24, 25, most code reviews, I think, for most of the audit firms are performed remote, and that's it's fine, yeah. And because also many of the teams are remote, and everybody's used to working remotely together in video calls, chat, and everything. In this case, the Mullvad team, there was in one place, so in Gothenburg in Sweden, and this is of course also fine. But what is even better is that we had two auditors, was Robbie and me, that could visit them, and this was really helpful, because the interaction with the developers on a personal level, but also, let's say, the easiness of asking questions or talking about things with developers, maybe not with one, but maybe a talk with 2 or 3, that helps a lot. So and this is something that I want to stress, and this is something that I think could be something for larger open source project as well. Just as a suggestion that this kind of local interaction, at least for a few days, would be very beneficial. And we did not do the full audit on site, but we basically were 1 week together with the actual development team. And and the side effect also is that the auditors are also in one place, meaning that even some after hours you have some discussions, and that also helps us really deeper understanding for a complex audit. And this audit definitely was a complex audit, and there it is really good also to be kind of slow to that. If Eric said about the threat model, it might sound a bit boring, for some people that say like, I want to find bugs and I want to go right into it, and I would call this more the bug bounty approach, which is also legit. However, if you review a complex product and you want to interact with people about this product, and you want to also report valid bugs only, then you need to do a proper discussion about the threat model, if none exists before. So you should do that, of course, with your co-auditors, so you're also all aligned on the threat model, with the actual developers, of course, and project managers. But I mean, also with yourself.
Especially discussing it with the developers is very often super fruitful, because in most cases you get the first few bugs for free, because you're challenging the beliefs that the developers have about the threat model. And quite often that's when they recognize they have some architectural or design issues in their code. And when you ask about specific implementation things during this discussion, you quite often also get something like, yeah, we didn't do it that way, but this way, which is not good. And if it's not good there, it's also probably buggy in these other 3 cases. And you can already start writing the report, right? It's always useful.
Yeah. And it's also good to talk about the threat model and as Eric said, challenge it. And that also helps you a bit as a kind of reality check. Yeah, when you dive deep into the technical details or into bugs. But I mean, the threat model actually starts not at a technical level, and it's also a bit of a reality check if it's done right. Yeah, I mean, there can be invalid threat models that exclude stuff that shouldn't be excluded. But on the other hand, I mean, as Eric said before, we, for example, had to decide are local users a problem or not. Yeah? Can they just pull the network plug? Yeah, then if they are a local user or have physical access, so maybe denial of service on the software level there is not that bad. Right? So. Or maybe it is. So, and that's what you discussed. But I mean, the most important thing is what must never happen. So that's actually a question that everybody, even the most technical person and the least technical person at the same time, they all should ask this question. Yeah? So, and what is also important, of course, is past vulnerabilities and their impact, because then you can also see how is the understanding of the project in general or so far, about certain things. And then I mean, at the end, what you want to find, of course, is security defects and vulnerabilities. Yeah, that's your job as a code auditor there. And for that one, and then also to avoid the discussions, the threat model again is important. Yeah, discussions can unfold with the developers. Yeah, if you are not on the same page about what is the bug and what's not. Or of course the internet, and especially in the case here of the OSTIF, where a lot of reports are published. What you definitely want to avoid is controversial, let's say, discussions about are these bugs valid or not. Yeah, so that's important. Get familiar with your target and also draft the threat model and write it down, and also discuss it. And that's reality to check it as well.
And usually these discussions are in the form that people want to downgrade issues you find and somehow define that they are outside of the threat model. And if you define the threat model beforehand, this is way easier to agree upon whether something is inside or outside. In the case of Mullvad, we had the other situation where we said, okay, we found something that's outside of the threat model. And they asked us to still include it and rate it as a high finding, which is, I guess, a nice approach to see that a vendor is not trying to downplay bugs, but to actually rate them as they are and make sure that they are addressed properly.
Yes. And the findings are they were distributed the following way. So we had 3 high findings, 2 medium, 1 low, and then we had 3 informationals. I mean, you can see the absolute number of findings is quite high, especially if it's quite low. The absolute number of findings is quite low, especially compared to the size of the code base. And that can be, in our mind, attributed to a very high baseline security. And also on the focus on, let's say, maybe deeper bugs that require more focus. And that's also something audit teams talk about. If you do audits, talk about that with the audit team, if they should go deeper or if it's more about broad. So if the resources are limited, for sure do that. We also always rate the findings by CWE, and I mean you can see here that the distribution, except for one, I don't know that by heart, but appeared 2 times. They were all, let's say, kind of different types of issues. Let's go to the first finding. we don't have enough time to go through all the technical details, so let's speed run a bit through it. This was a very interesting one because it was the one that crashed, or that is an issue that happened even though, for example, I would claim that nearly everything was done right in the Rust code, meaning, yeah, that it was memory safety was of high value, and I don't think we found any kind of memory corruption. Also, but we found a corner case, and that is that a signal handler's alternate stack was too small. And what that means, I want to, and that was present in the Mullvad daemon, yeah, and it was present in the crash handler. So what that means is that there was a crash handler installed that was getting installed and catching SIGBUS, 6FPE, 6SEC, and SIG-IL 6 signals. These signals are, when an application is crashing, they are triggered. And if a signal handler is installed, then the signal handler is run, and usually it should do something like lock the error or gracefully exit and so forth. Yeah. Not all of them, and you see here 6 segmentation fault. Okay, if you have a segmentation fault, it's kind of a hard crash and might also be a security issue. But there's also others, yeah, SIG FPE that could happen with division by 0, depending on some conditions and how things are compiled. But yeah, anyhow, these crashes can happen. Now we have to say that we didn't find a way to trigger them. But if it was triggered, yeah, the interesting point was, okay, then here the signal handler is installed. There's no way around using safe Rust to install that signal handler, yeah, because this is a low-level operation, yeah, just for the record. But what happened is that signal handlers, they need to have their own stack. Why do they need to have their own stack? Yeah, because they run when something has crashed, so the original stack might be corrupted. So yeah, the data of that signal handler needs to be stored in a location that is kind of clean. And for that one, here the developers use a heap buffer, yeah, and a vector in Rust. Yeah, I mean, it's very an innocent bug, yeah. So I think really everybody could have made that mistake. So they used the libc 6 stack size. Yeah, this is like a default size. I think it's 4 on x86 64. It was 4 kilobytes, so page size. And they use that buffer and say like, this is now a new stack, yeah. And you have to call the sig alt stack. Yeah, because you have to yeah, let's set that stack on that process. Now the problem is that this stack was too small for all cases, meaning that if a signal is actually triggered, the stack could actually corrupt the heap, and that is of course pretty bad. Yeah, because stacks on the heap, because then with a normal crash, you can get an potentially exploitable condition. Yeah, so that was a pretty interesting bug because it went kind of under the radar of the normal threat model, especially if you write a Rust application, that you don't basically think about something could corrupt the heap if you didn't do anything unsafe, obviously unsafe. Yeah. But yes, your crash handler would kind of crash again, potentially. I think it's something that's not expected for most people. There was another issue, which I think then there was a bit of a different, let's say, or there's debate about it, if this is how exploitable these conditions are. But I mean, we went with this is undefined behavior. There's signal handler was using non-async safe functions and non-reentrant functions, meaning that this is the signal handler here, and as I said, the signal handler should kind of printer backtrace some log. The problem is a signaler might be invoked in an operation, let's say in a log operation. And if then from this log operation, inside the log is called again, logging, there might be invalid states, yeah, because some of these functions, output buffering and so forth, they have like internal buffers or internal states or pointers and so forth that are not safe for being caught again while they are running. Yeah? And that is undefined behavior. It might be hard to exploit or even trigger. Yeah. But this is still undefined behavior. And I mean, as I said, there could be things happening, corruption of pointers or other things, depending on the function that is used. I think here, the most of the issues should be output buffering. But even then, yeah, better be safe than sorry. Eric, do you want to explain that one, the side loading?
Yeah, I think from a technical point of view, it's not that interesting. It's quite similar to DLL sideloading. The Windows installer is picking up an executable that's in the same file directory. And if it's there, it will start executing it. And this is the issue which for us was outside of the threat model, because if an attacker is able to write an executable to a third path, the client machine, then I would consider that machine compromised, right? There are these other examples where the installer might be on a file share and the attacker is able to access the file share, and right. But this is something where we would have said, okay, with the threat model given, we would only do that or only write it down as an informational. But when Mullvad requested us to rate it properly because it was an issue for them.
Yeah, and I want to say that this is really a good example for a sensible approach to real-world security, because theoretically, yeah, I mean, if an attacker places malicious files on your system and then somehow it's executed, might say this there has been a problem before the execution. However, yeah, if you visit a website and you download this taskkill.exe, or maybe the website has auto-download and downloads it, yeah, and it sits in your download folder, and you didn't execute it, but then you download the trustworthy installer of your favorite VPN client, and then you execute that installer, and unknowingly to you, it will execute also this malicious file. I mean, there can be practical attacks, obviously, yeah. So, and that has happened before with DLL sideloading as well. Or if you think about the installer sits on a network drive, and there's also this weird taskkill.exe that you won't ever execute, but you execute the installer, then also that's yeah, kind of a practical attack that is in our mind also realistic. So. The next one is medium severity only. However, it was still an interesting one because it also cuts into this domain of operating system and how networking works, for example. So we found a leak of the virtual IP address of the tunnel device, meaning that if you have a VPN tunnel, inside the tunnel, you have, let's say, an internet protocol address that is inside the tunnel and not visible normally to the outside. In most VPN scenarios, maybe it doesn't matter if it would be visible or not. But in the case of a privacy, let's say, preserving VPN use case, knowing that IP address, and if it doesn't change that often, might give you some evidence that a certain user is you could kind of learn something about the user identity. And this affected Linux and Android. And what happened is that the Linux kernel, we found a quirk kind of in the Linux kernel network stack. I wouldn't say that is a bug, because probably there's some kind of use case for it. But the point is that the Linux kernel, if you have multiple network interfaces, it will, and you will ask on one interface for a certain IP address, like, do you have that IP address? Then it will answer even if the IP address is on another interface, that you're not even, that's unrelated to it. You use this ARP, address resolution protocol, for that. And that's broadcast. It's super old protocol. I mean, base of all the discovery of local devices, IPs. And so you could, we found that you could just query for the Mullvad range and eventually you would get a response. And then you're like, aha, this user on that system is using Mullvad VPN, and also, aha, this is probably this user, or it's the same user as yesterday. And yeah, I'm not that great at doing diagrams, but so this is, if you imagine there's a victim device, it has a VPN connection with encrypted traffic, and the attacker can just query that device and say like, hey, do you have that VPN IP? Yeah, that is, should be inside here. Yeah, so the interface on the right, unrelated to the interface on the left, but the Linux kernel would still, let's say, answer that. And in the report, you find a kernel setting to turn that off, so at least. And I think Mullvad also filed like a kind of so submitted that to Android, because Android by default also does that. And it also affects, of course, other VPNs and devices. Yeah, so the next one, that's also medium severity, but also a very interesting one. It's a bit more complex. So let me start with some kind of preconditions that also JJ asked me to put in, because a lot of people don't realize that there are certain conditions where a VPN setup is kind of in danger, because if an attacker has two critical network positions, and these positions are, they can observe or even inject into adjacent networks to the VPN client, where they can see the encrypted VPN traffic, but right at the source. They might not know which user that is or whatever, but they can see there's somebody using a VPN, and then they generate and receive and submit traffic. And then at the same time, they are also able to see the tunnel exits. Tunnel exits, or even the target of the communication. If you think about the one of the first slides, this diagram. So, and if they can see both of them, then you can do things such as traffic correlation, but also there's an interesting injection attack that we found. I have to say that this was found is also by others a bit before, a few years before. But yeah, we kind of want to feature it, and I think we added some aspects to that. So I painted this great diagram. So imagine you have a Mullvad client, and they have a VPN connection with the Mullvad backend, or a VPN backend, and they have an internal IP. So if they have an internal VPN IP, of course, there needs to be NAT, network address translation. And so let's say they want to contact google.com. So what happens is they go over the VPN, they go out of the VPN, but the VPN, of course, changed their IP address, so nobody knows that it's this client. So they go to google.com. Google says like, oh, okay, I have a request here from this exit IP, and they send back. So everything's great, right? Everything's protected. However, if an attacker kind of assumes that there's a Mullvad user that is talking to google.com, and because nowadays, Quick and other protocols use UDP. You know, there's a state on Mullvad that says like, okay, if the UDP packet comes from google.com, I will forward it exactly to this client. I mean, must be, right? How else do you receive the response? So if the attacker knows that, or wants to know google.com, they can kind of flood and they can like fake the IP of google.com, fake the answer, yeah, and they flood the exit relay with UDP packets with different source ports until they hit one. And if they hit the right one, then this traffic will be delivered to that client here. So now if the attacker can also observe how much traffic happens here on this VPN tunnel at the client, they can kind of easily correlate and say like, okay, there's I send a lot of UDP packets and then there's a lot of traffic here. Yeah. So this is a kind of de-anonymization attack that is not really a fault of Mullvad or any of the others. It's just how NAT and how this networking stuff works. Yeah. So I would call it maybe design weakness or something that is the limit of what maybe the VPN in this way can provide. That's a pretty interesting attack that we found. It was found before, or at least a variation of that, called server-side attacks in the Usenix paper, blind in on-path attacks applications or to VPNs. Yeah. So that's after researching for previous work, then we found that as well. We didn't know that before. What we found is that with increasing usage of modern web protocols, HTTP3 quick, and it's very quick, relies on UDP. You can also run this attack with TCP under some conditions, but yeah. And preconditions is of course to reiterate, attacker can observe the network traffic of that client, just not decrypt it, just observe it. And they have a list of potential Mullvad exit IPs, and they have the ability to spoof IP packets with a source IP of something on the ClearNet, some interesting site. Let's say you are, in a country that doesn't like you to visit a certain website, and the authorities there want to know if you did that. They could try to run this attack, because they usually also control all the ISPs and everything. Yeah. There's a slight counter to that. Mullvad has something called data, and that is traffic generation. So they kind of generate random traffic on your VPN connection that is kind of fake. Yeah. And that can at least partly mitigate it. I mean, you could probably run some statistical attacks, or analysis on that, but at least it will partly mitigate it by having this kind of decoy traffic. Yeah. There's a similar one that we don't go into detail, but by varying the MTU on the path between the exit and the target internet host. And there you can, the maximum transfer unit, you can also see if data is not used in normal VPN. You can see it like WireGuard. You can see that the sizes of the VPN packets change also. And then you can also de-anonymize kind of the user. Same preconditions as before, the one before. Yes, so some recommendations. I mean, you can read the report in detail on all that it's public on the website of ostif and also X41. So for the high security issues, I mean, increasing the stack size for the signal handlers will mitigate this corruption. Also, not doing complex tasks in signal handlers is also something that as it is from a security perspective advised, and only use async safe functions. And you can find that in man pages at least on Linux. There's a dedicated man page for this one. And Yeah, for the side loading, of course, restrict the execution of utilities to trusted code paths. The medium severity ones, if you randomize the virtual IP addresses per connection, I think that was done. Of course, this kind of leakage attack against the identity or pseudonym of that user is not possible. Also this kind of obfuscation techniques to mitigate this NUT-based de-anonymization can help. We think that it's important that users know these limitations. Yeah, even the Tor network has a similar kind of limitation. Yeah, if you have if you monitor, let's say, a hidden service and then also a Tor user and you suspect they're using that service, you can run similar attacks. Yeah? So it's, I think awareness is the key here. And yeah, for the low severity issues, I mean, it's the same as for the other one, MTMU related. So that could be mitigated by padding packets. Yeah, coming to the conclusion, the target application demonstrated a high level of security. That's what made it, let's say, interesting audit, because we had time to focus on the non-standard stuff, and that contributes also to overall security of everybody. Yeah. So, and I mean, positive observations, definitely you could see safe coding patterns and design patterns also having an effect, a positive effect on security. Also regular audits, I mean, they read out all the standard things. Yeah. But on the other hand, of course, there's always something to find. Even due to changing, the world is always changing, and also something just that is, let's say, was hidden for a while. And I think having a good baseline security level, which is something that the OSTIF here is also what we like about the OSTIF, is also the key to advancing security on the non-trivial stuff, and to go for deeper issues and enhance the security of protocols and also the awareness and about secure design. Eric, anything you want to add?
No, I think you summed it up quite nicely.
Okay, and then I guess that's the presentation part. Thank you.